Okay, we were looking at these elements called nilpotent elements, which is an element that when you raise it to some positive integer power, you end up with zero, and this would be a non-zero element here. So we would call a nilpotent element. So question number 14 in chapter 13 asks us to show that the subset of these nilpotents within a ring, within a commutative ring, form a ring themselves. So what we really needed to do here is show that it would be closed under multiplication and subtraction. So in order to do that, we've already got one arbitrary element here. Let's get another arbitrary element, and we're going to raise it to the nth power just because they don't necessarily need to be raised to the same power to be nilpotent elements here. So closed under multiplication is not so hard to show. Basically, we need to show that this product of A and B could be raised to some power and would get zero. That would show that this element is also a nilpotent element. In other words, the nilpotents are closed under multiplication. So if we just raise this to the mth power here, we have a to the m, and then a to the m equals 0 times b to the m, but 0 times anything just gives us 0. So this tells us that AB is also a nilpotent element. Closed under subtraction is a bit trickier. So we're looking at this element right here, and we want to show that there's a power we can raise this to that will also give us 0. This one took a little bit of experimentation and thought. We also have to stretch back into the binomial theorem and remember a little bit about what was going on with when we have these two terms and we're trying to expand them. The first term here would be m plus n, choose 0 or choose m plus n, however you want to do it. Either way, it equals 1. I'm just writing this down for the pattern. Clear, that's a plus sign. And then we would have a to the m plus n would be right here. I'm going to write it as this, and I'll make that clear in just a second. Again, this would be a to the m plus n, but that would be the same as what I've just written. And we'd have a b to the 0 there, which would not matter. Maybe I'll put it in there just for so we can see the pattern a little better. And then because we have a minus here, we're going to alternate signs. This would be m plus n, choose 1. We'd have, I'm going to keep that a to the m. So the powers of a are slowly going to go down one by one, and the powers of b are going to raise up by 1 each time. So this is going to be a to the m, a to the n minus 2, b squared, and so on. So this is going to continue. At some point, we're going to run out of n, I guess you could say, so that we're going to have n minus n, a to the n, and so at that point we would just have a to the m. So the coefficients actually aren't so important here. I'm just going to scribble this here so we can bypass that. At this point, we would have a to the m, b to the n, and then we'd have plus this, maybe a minus again. It doesn't really matter, some coefficient here. A to the m minus 1, we have b to the n, b to the 1, and so on, all the way down to the last term would be some coefficient. And I'm really being lazy because I just didn't, this would be m plus n, choose m plus n. I really could have thought that through, but we'd have an a to the 0 here, and then b to the n, b to the m. So why go to the trouble of splitting these powers of a apart and then at some point switching over and splitting these powers of b apart Well, because we know these two relations, we know that a to the m equals 0 and b to the n equals 0. So notice that each of these early terms has an a to the m in it, which would then become 0, all the way up to this term. Beyond this term, we're not going to have an a to the m in it anymore. But at this term, notice we have both of these would be equal to 0. But from then on out, we have a b to the n, which is also equal to 0. So because of that, every term in this binomial expansion equals 0, and the whole thing equals 0, which tells us that this little guy right here is a nilpotent element. We've found a power that we can raise it to that gives us 0. And since the nilpotents are closed under multiplication and subtraction, we do know that they're a subring. Where did the commutativity come in, by the way? This binomial expansion would actually get a little messier to write out if we didn't have commutativity. The a's and b's would be all jumbled, and we wouldn't necessarily have m of the a's together or n of the b's together without that commutativity when we would distribute this out in a mangly mess if we didn't have that commutativity. So that's why we need it in order to, not because it's nice, but we actually need it in order to get m of the a's together or n of the b's together. Okay, and let's now move to 13, 15. So this is asking us, show why 0 is the only nilpotent element in an integral domain. So let's assume that we had let a, which is non-zero, be nilpotent in an integral domain. So we're gonna go for a contradiction here. So a is not 0, but it is nilpotent, which means that there's some positive integer n such that this is true right here. N certainly can't be 1 because we know that a is not equal to 0. So n is at least 2 here. We're going to say another thing too. We're going to let n be the minimal positive integer. I'm just going to write where n is minimal. And what I mean by that is, let's say that a squared would equal 0. Well, if that's true, then we'd also know that a to the 4th equals 0, and a to the 6th equals 0, and so on. So whatever this positive n is, we're going to make it minimal, so as low as we can go, so that if we did a to the n minus 1, it would not be equal to 0. Or a to the n minus 2, it would also not be equal to 0. Once we have this, all we need to do is write a to the 1st times a to the n minus 1. And that's going to give us 0 because we know that a to the n equals 0. So we can split it apart like that. But here we have two non-zero elements being multiplied together to get 0, which is not possible in an integral domain. An integral domain would have no zero divisors, but we've just found at least one zero divisor. Lowest case, we know n can't be 1 because of this again. If n were 2, this would be a times 2 minus 1 times a equals 0, and still that would violate the rule of an integral domain that you couldn't have a zero divisor. So in any case, we found a zero divisor here, and that is a contradiction.